a program that outputs a response that was not developed by a coder.
Interesting. Okay. Like the idea of AI, thank you very much, Kevin, is how can we make machines more, or just intelligent, okay? And intelligence here is in the sense of adaptability, okay? I want to be able to create a system that, given different inputs, will be able to like just on the fly know what it should do, okay? Right now we go to a paradigm where like most of that is just done using data. So like we learn most of those patterns and those things that we should know using data, which is really where machine learning lies in. But for a long time, people thought that it would be possible to create truly generalizable systems that would all function using rules, essentially. Okay, so the idea of symbolic AI. I'm able to create a set of rules, and based on those rules, the system is able to just adapt on the fly. So this happens, do this. This happens, do this. And the idea was that if I'm able to list the procedure well enough, okay, and with enough details, I'd be able to just adapt to whatever I want. I think we all know that we are way past that now, and mostly because it's just not really feasible to do that for most things. Like for example, how do you list the things that you should check for? For example, if you're trying to identify a cat, for example. Like how do you know that what you're looking at is a cat? Or like me, that I'm not a cat, for example, okay? There's way too many little things that would need to be encoded, and way too many things that evolution encoded already in our brains, okay? That makes it so for us, it is trivial to say that, okay, yeah, I got a human being in front of me here wearing a red, like a wine sweatshirt, okay? I got someone over there wearing glasses, another guy, and I got a girl sitting here, for example. And none of these people are like cats or dogs or whatever, okay? So, it's impossible to do it symbolically and just encode a set of rules. So machine learning is when you start thinking about, okay, since truthfully I cannot do that with rules, can I instead try to make it so the patterns that the patterns that I care about, I'm able to model them using data, okay? And so that's where we start thinking. With machine learning, just classical machine learning, like a lot of like techniques that you might have heard of, like linear regression, logistic regression, et cetera, techniques that we'll see shortly, the idea really is just see, am I able to identify patterns in data, first thing, and then am I able to model those patterns? If I'm able to model those patterns, and if I mark it, that'd be great actually, in such a way that I'm able to predict what will happen, okay, what should be my correct response given a given input, then I'm happy. That means that I'm able to actually use that model that I created to predict things in the future. Is everyone following up to now? Perfect. Then there's deep learning. Deep learning, okay, comparing it to machine learning, they both have learning in the name, so they might sound similar, and they are. But deep learning, as you see from the picture here, is mostly a subset of neural networks, okay? So when you think about deep learning, typically what you're thinking about is you take a neural network, and typically you're going to be thinking about stuff like, well, you take any neural network you want, and you start adding more and more and more and more layers to that. And the idea is the more layers I add, and we'll cover neural networks very soon when I go into the application stuff. The more layers you add to your system, to your neural network, the more complex functions it then become able to model. Okay. So that's the idea. On its own, that might not be too useful because, okay, I just identified terms, but what exactly do you do with those? Typically, when you're working in AI/machine learning, there's like a few categories of problems to be dealing with. Okay, and so that's what we call a taxonomy of machine learning. You could be in a supervised learning context. Okay, supervised learning is when everything is going well and you're happy because, for the most part, a lot of the classical models we have, and like even stuff like neural networks typically, will assume that you already have labeled data to use. So you're able to check, okay, I did that, how wrong am I? Okay? If you're able to do that, so if you have labeled data to use, you're in a supervised learning context. Like you're in business, that's amazing. Okay? The other category, okay, that you could have is unsupervised learning. So that's that's when things went a little bit wrong, in the sense that you have data, it's available. But the thing is, all the classical machine learning models you're going to use most of the time, and even like deep learning stuff, is going to expect you for the most part to have labels. Which means that if you don't, how do you directly assess how good you are, how far you are from like what you should actually get? You don't actually know. How do you assess that when you don't even know what you should get, right? If you're in that realm, you're doing unsupervised learning. Okay, we'll cover that a little bit further after. But if you're in the unsupervised learning realm, you're going to be forced to be much more explorative in your approach. Okay. Then we have reinforcement learning. Who has an idea already what reinforcement learning is?
So you're given like I think you're given like a test and a training set. So that test set already has like defined things. Let's say like as pictures of cats versus not cats, right? Mm-hmm. And then you use some type of activation function, and then you compute that activation function. Basically calculates. You use a couple of those, the layers of the neural network, to calculate on the test data whether it's a cat or not a cat. Let's say you get it wrong, right? It's like 47% sure it's not a cat, and it is a cat. Your cost and that value would be 1. Your cost would be like 0.67%, right? Like, or something like that. And then to adjust for the cost and make the cost 0, you use something called gradient descent. So basically, whatever the parameters are, you basically find where the rate of change in the function is 0. I know that's kind of hard to explain like
No,
in a sentence, but
it works.
yeah, but that's kind of how it works, I think.
What's it?
Nyako. Nyako.
Nyako.
Greek name, man. They're hard.
Thank you very much, Nyako. What you described is actually, it would be better described as supervised learning.
Oh,
Okay?
okay,
Yeah, because like in what you just described here, and like thank you very much for trying. In what you just described here, you actually have the answer. You know that there are cats, you know that there are dogs, right?
Yeah.
And so you'd be trying to like use those input features that you have, and then you'll be predicting on that. Reinforcement learning is slightly different because in the way it's made, okay, and like we'll cover that quickly after. But you start the assumption that instead of trying to like attack a problem directly with like the right answer, instead you start with like a set of elements. Okay? First you're gonna have an agent. The agent is like something like you and me, like someone who's hopefully intelligent. But since you're doing machine learning, it's gonna be your computer. So like it's gonna be some kind of automated agent in the machine. You have then a set of states. Like you and me, depending on where we are, we might take different actions, right? So if I'm here at school, there's some actions that I would do or wouldn't do that I wouldn't do if I'm at home, for example, or if I'm in a restaurant. So where I am will affect what type of actions I do. So we have a state, which could be identified as like, in this case, where I am. And then we have the set of actions that I can do, which for a reinforcement learning context will be just like what exactly we allow the system to do. And then finally, we have the idea of a reward, which is the thing that's gonna motivate everything, okay? Where, depending on different states and different actions, we want to assign, let's say, a penalty, or actually promote some behaviors. So maybe if I'm at home, for example, and I want to make sure that my agent studies, like let's say my agent is me, okay? If you go home and you use TikTok, I'm gonna assign a reward of like -10. I don't want you to be using TikTok. On the other hand, if you spend like an hour studying, I'm gonna give you a reward like +20, okay? Finally, we have something called the policy. The policy is a thing that assigns, let's say, probabilities to different actions. And the goal is to find a policy that will maximize your reward. So I want to make, in this context, for example, in a very simple example I gave, you want to make it so that if I go home right now, our policy is not me going on TikTok, or not me, I don't know, like just binge watching YouTube, but me actually studying. So we want to maximize the policy that makes it so I study, right? So that's the idea of reinforcement learning. And the thing that's really nice with it, we won't cover it too much in detail, so it's fine. But it's like, technically, you could formulate any problem you want as a reinforcement learning problem. Okay? You shouldn't, but you could. And then finally, we have hybrid learning. Okay? It lies somewhere in between those two. Okay? And it depends on like the kind of data you're doing. Here I made a clean split between supervised learning, where you do have labels, and unsupervised learning, where you don't have sometimes you have situations where you actually have labels, but only for some part of it. Okay, so let's say you're trying to build a classifier for breast cancer. Okay, you're trying to build a classifier for breast cancer, and you have a lot of data, like huge databases of different cases of breast cancer that were identified or were not identified. But the thing is, you didn't think of actually classifying those, like labeling them. It would take way too much time and be too expensive for you to actually classify them. Okay? So you have a vast majority of data that is not classified, but that could easily be numerized in the sense that I could easily just take the pictures, send them online, but I don't want to take the time to actually label them. So that would be my unsupervised part. And then I can take, then let's say in the same case here, I have my, like a more modern system, okay? And at some point in the past, we started actually labeling the thing properly in a database, which means that now we have part of it which is supervised. So the vast amount of it is not supervised, but I do have labels with, I do have examples with labels. Is all that making sense for now? And so in a semi-supervised context, the idea would be, maybe I could let you try to guess that. What do you think would be a nice approach for a case like this, where you actually have some information with data, like labels, and some cases where you don't? Like what would be an intuitive thing to do?
I would train the labeled ones at first and use supervised learning, and then use unsupervised learning train. Actually, no. I'll try to use unsupervised learning to train the whole data set and try to and then to check the prediction results with the label ones and to make this input into the model and to improve the model.
Well done.
What's your name?
Yuma.
Huh?
Yuma.
Yuma?
Yes.
Thank you, Yuma. So that's exactly it, okay? I start with training a model on supervised, like on the supervised part of my data. Because that's easy. I can, like, there's a bunch of techniques that I can use to do that really neatly for me. And like, if we're doing images, I'm probably gonna be using like some kind of like CNN, but I can do that fairly simply. And then I use the CNN model that I have, and then I try to use it on inference, like I try to use it to, and I pass the unsupervised part of my data set, okay? So I add the trained thing here, and then I pass those things that don't actually have the labels into it. So logically, this will give me like classifications, right? And typically, depending on which approach you use, but like if you use the CNN, you actually have like something called confidence, which allows you to know how confident you are about your classification. Then, on those cases where the model was actually highly confident of its thing, I can then give the label of the model to it, as what we call a pseudo label, okay? And then train on a now bigger data set, okay? And then I just keep doing that iteratively. So I start with the supervised part, I test on new data, like that is unsupervised, then I go back here, I add the new data that I'm confident of, and at some point in the process, a human will actually come in and like verify those things to make sure that you're not just adding things like, you're not just reinforcing patterns that the model is already seeing, okay? So you add that in at the same time, and you just keep doing that until you have an actually really good model. The other case you could have in this hybrid learning thing is self-supervised learning, okay? Self-supervised is really interesting because I don't actually have labels in this context. Okay, I don't actually have any labels at all. But there's one thing that I do have, and that's the structure of the data itself. Okay? If I asked you to give me an example of something, okay, it could be anything, but I just try to think machine learning, a thing where the structure of the data itself tells me information about the data. What do you think of just like off the top of your head? Okay then.
TV shows?
That's really interesting. Okay, TV shows, yeah, okay, that could actually work. Video, for example. Like just, not necessarily TV shows themselves, but just video in general. The context of the thing, well, okay, no, with video is like a bit more complex than that. I probably need to. Let's go with something a little bit simpler and low dimensional. Let's say text. Text, okay? If I give you something like a sentence, okay, even if I don't give you any labels, okay, I put, I have a blue car. In this context, blue is intrinsically labeled by like the structure of the sentence, because blue, I really wish I had a marker right now. My bad.
Go on.
Oh, thank you very much. Okay. No. Okay. So if I write something like, well, I'll use red now because, well, I have a red car. Okay. In this context, okay, red is directly modifying car. Like red is labeling my car. I'm saying that the car is not just any car, it's a red car. Okay? But on the other side of it, the car here, okay, so now it's giving me information about the fact that red here is not just any state of red, it's specifically the type of red that pertains to color. Okay? On the other side, if I say something like, I am seeing red. Okay, like I'm really angry. I'm using the same word, right? Okay? But in this case, the context of the sentence itself is changing the meaning of red from the idea of like a color to the idea of like now it's an emotional state, like I'm angry. And so the structure of the sentence is my labeling. And so if I let a system just learn on a bunch of text on its own, learn like what makes it likely that a word will appear next to another, I'm able to have something that learns that language from me. And then I can just refine that in a supervised learning context. That's how things like GPT, for example, for the most part are done. They're trained on like huge chunks, bodies of text, which is self-supervised. And then at some point you include some reinforcement learning where I'm trying to enforce guidelines, like make sure that you answer in a certain way. Okay? It's like that's how you can jump and like go from one category to the other. Yes?
Yeah, my friend told me about like he was telling me about some vector like that ChatGPT uses like vectors, like the vectors are like similarity, like it's like red and like I don't know, like red and blue, right? How many times are those sentences like said in the same, how many times are those words said in the same sentence? Or like father and son, right? And then it'll realize the similarity, right? If the like if it's said a bunch of times in the data, then the distance will get shorter or something. I'm not too sure how it works.
Like the thing you're describing is called an embedding. Okay? And the idea is that you want, like, here I wrote it in text and like I didn't bother going through the math because if you understand the intuition, it's like kind of fine. You can look at that on your own time. But a computer cannot understand text, right? Which means that if I'm trying to like give that to an actual machine, like AI model, I need to give, well, vectors of some kind. Okay? For a long time, it was done using like one-hot encoding, which means that I just had a big map, okay, where the first word was equal to the second word is equal to something. And then I literally have just a huge vector, which is as big as the number of words I care about. And it's going to be 0, 0, 0, 1 at some position and then 0 everywhere else. And the goal of that is that it would allow me to just index directly into my table. Okay? Now like you can still do that, but like a lot of times it's just more efficient to have like actual embeddings that contain information themselves. And so then the embeddings become like kind of like just probability distributions for the individual word itself. If what I just said didn't make sense, that's fine, you don't really understand it for the rest of the presentation. So yeah.
Does ChatGPT tokenize each word or does it split each word?
It tokenizes. Like they have a built-in tokenizer. Like they have their own tokenizer for GPT. Yeah. And tokenization, for those that don't know, is like, yet again, I'm using it at a high level here because, well, it makes sense. But ChatGPT probably wouldn't have seen, for example. When you give some text to GPT, those words here will be lemmatized and stuff and transformed to like words that I don't need seeing. Just with I am see red, I can see the context of, okay, the word is the verb see being used here. So I have see here, and so I don't need to keep track of like all the different conjugations of that. And then this is embedded to something. Okay? And then there's gonna be like, here I have, if I had a longer word, let's say, like me, for example, my name is probably not something that he knows. Okay? This would probably be like split in chunks. I don't know exactly, but it would probably be split in chunks, and then the bits would be individually embedded. Yes?
Is a token a vector?
The token is, no, the token is essentially like just this would be the token, for example, and is token. Then the vector, the embedding, which contains like this random values, well, learned values, is what the model actually sees. So let's see how to do that. Okay. Okay, so I'm now gonna fly over a lot of stuff. So supervised learning. Okay. That's a lot of stuff that we already saw. There's two main cases that have in supervised learning. Regression case, where I'm trying to estimate the numbers. And here, the example that I have is, you take a drug, okay? And you're trying to see, based on the dosage, how do you say it? Basé sur le dosage, based on the dosage that you give people, my bad, okay? You want to see how well they recover. So the higher this is, the better. And you're trying essentially to predict, okay, based on the characteristics of a given patient, how much I would need to give them, for example, to have them achieve a given level of recovery. Okay, that's one thing that you might try to do. Okay? So that's the first type of supervised learning. The other kind is classification. Okay? You're just trying to assign labels. Discriminative models. Okay. I said I wouldn't go too much over that. The idea is you can have models that just directly try to predict the probability of being in a given class, given that you're X, which is what we call a discriminative model. Or you could have models that use, okay, who here knows what Bayes theorem is? Okay, so since there's not many of us, I won't go too far. But that essentially use something called the Bayes theorem to compute something that can approximate that, well, that gives me that, okay? And yeah, so that's a generative model. Based on what you're trying to see to get, if you want to have something like confidence, you want to go with a discriminative model. If you don't really care and you just want a more accurate thing, you just go with whatever works for you. So that's a dot-cat classifier. Some key metrics that I think you should all know at the very least. Okay. First one, the idea of accuracy. I think everyone here probably knows what accuracy is, so who can try to give me a definition? Okay.
How close you are to your target?
Pretty much, yes. The idea is, just take your classifier, it makes a bunch of classifications. What is the ratio of right against the entire thing, over the entire thing? That's your accuracy. Accuracy can be deceiving for many reasons. If I give you, for example, a data set where, let's say we take a breast cancer thing, okay? And most people are fine. That's my quantity of people that are fine. Let's say I have 9 full samples. All these people are fine. Well, fine, okay? And then we have 10 people that actually have breast cancer. If the only thing I cared about was accuracy, my model could literally just assume all the time that that person was fine, and it had a really high accuracy, okay? Which is why you typically want, when you're doing classification, to use it with other metrics, okay? If you care about, for those that are right, you want to make sure that you can be confident that they're right, you're going to be caring about precision, okay? Which is a measure, which is a ratio of, for all the positive cases, how many of them are actually should be there, positive. Then we have recall, which is what you care about if you want to make sure that you identify all the positive cases. Okay? So there are cases like here in the breast cancer case, it might be more important for me to know that I might be fine with testing people that don't have cancer because that's less big of a risk than letting someone that doesn't have cancer go. So in this case, I would probably care about recall more. And then there's something that I forgot to put there, like the F1 score, which takes the harmonic mean of the two. It's just when you care about both, actually. Okay. And finally, there's a confusion matrix, okay, which is that big thing over there. It's not that scary, honestly. You're going to be using confusion matrices for the, like, most of the time when you have more than one class, more than two classes to care about. And it gives you, just like at a glance, okay, I see that all those on the diagonals are those that are properly categorized, okay? Then when I go at A, B, I see that it was B, but it was classified as A. It was C, but it was classified as, there was one observation that was a B, and it was classified as a A, and like you can read those numbers that way. Okay, so what number it was classified as and what it actually was. And then here, when I read the column, I see what like it actually was, so still A, but where did I go? Okay, so this gives you like at a glance a measure of how well your model is doing classification-wise. And with that information, you can see that, okay, maybe you got a model that does some things better than others, and then you go from there. Sorry, it's, okay. So, let's do it then. Okay. Does everything make sense up to now? Yes. As you'd expect, machine learning is a really dense field, and you have to believe that like, over there's a lot of stuff I glanced over. Okay, you're gonna need to learn that stuff on your own if that interests you. Okay, but that's the idea. Here, now we have the idea of proper fit and bias variance trade-off. Okay, if I tell you that, like I give the analogy of like a machine learning learner, like think of a student. Okay, and we'll go into surprise case because like that's typically where when you can model those kind of things. Okay. Then you could easily think of like 3 students, okay? Let's say you're about to take your applied linear algebra final or something, okay? You're about to take that. And the teacher was kind enough to give you practice finals to work on, okay? You could have the overly confident student who's like really, like he has the assumption he already knows everything. He knows that he can do it. And for that reason, he doesn't study enough, okay? There's there's information that he would have learned and like about what exactly is going to be tested that he would have learned had he done more of the test, but he doesn't. Okay, but for that reason, he has a poor performance of the test in the end. Maybe not terrible, but like in the end, has a poor performance. On the other side, we have a student who doesn't really believe in themselves in that way, and so they just try to like memorize the entire thing. In the end, they're so good at like just doing the test that like, yeah, okay, if that test was given exactly, they'd have a 100% no question. But did they understand what they were doing? Not really. Okay. And then for any cases like that where I have 2 extremes, you can imagine that there's somewhere in the middle, a sweet spot. And that'd be the person that learns enough of the patterns found in like those tests to know what is expected, and that is then able to generalize from there. That analogy I just gave, if you just think about those different students case by case, you have the idea of the bias variance trade-off. Okay? If you're like really confident about yourself, okay? If you are like rigid in your assumptions, let's just say it out, okay? If you're rigid in your assumptions, I know I can do it, and for that reason you don't study, you're gonna be a really high bias model, okay? A really high bias model. This is typically stuff like linear regression. Like linear regression doesn't really care about the data, it just assumes that there's a line to be found, and it finds a line, and screw it, okay? That's a high bias model. On the other hand, if you don't really if you're not making any assumptions, and you're a more complex model, then you have a high variance. You can imagine the student I mentioned that wasn't sure of their abilities. If I give them different tests of sets, like different tests of practice tests, they would memorize those as well. So they'd still get really good, right? But based on what exactly you give them, they're gonna learn different things. They're gonna memorize different things. So you get a high variance model. And somewhere in the middle, you have the person that learned enough, so like was flexible enough to learn just the right amount to bring those 2 at the minimum. Okay? And the idea of the bias variance trade-off is like a key idea in machine learning, like the idea of trade-off in general. Typically, the more complex your model is, the more you can fit the data easily, but the more there's going to be variance associated with it. On the other hand, the less complexity you have, the more assumptions you can bake in, and the stronger your bias is going to be. So if all that made sense, and I know it's dense, sorry, you're good. So I'm going to skip over a lot of this because mostly supervised learning is the most important thing in machine learning, one of the most important things, which is why I put it first. If you understood this concept, you're good. So here we have the idea of unsupervised learning clustering. Here you can see I'm just going to skip over this. Yes, I'm just going to skip over this. So, who has already heard about backpropagation? Just to see. So, before going into neural nets and backpropagation, would be good for you to just check on your own after. And then we're going to go to neural networks. So, thank you for following till now. We have linear regression. That's a model that fits a line to data. That's a y equal mx plus b thing. Okay. But with linear regression, what you want is to be linear in the coefficients. So you're gonna have your coefficients, your data can be whatever you want, but your coefficients is what you're trying to get a linear regression. What I'm saying by that is that if I have something like y is equal to, typically we use beta just because that's a tradition. This here, b1 x plus b2 ln of x, okay, something like that. This is still linear because if I replace that by y, y1, let's say, that by y2, that's like the typical linear form you're expecting, right? We are linear in the coefficients we want, so we are linear regression. Which means that the fact that I'm telling you linear regression doesn't mean you have to fit a line through data. Okay? If you modify the space you're working in, technically you're still fitting a line through data, but when you project it back to the actual space like a traditional coordinates, now it's going to look like a curve or something. So it's still a really flexible technique, and you should know it for that reason. Like there's many contexts that like even without that, if you just fit a line through data, it's going to work fine. Then you got k-nearest neighbor, which is another really intuitive algorithm. You just take your entire training set, store it, and then at inference time, when I give you something, you just find which are the points that are nearest to that point, the k nearest neighbor. And then if you're trying to do regression, you're going to take the average of those things. If you're trying to do classification, you're just going to take the most popular class. Okay. Then logistic regression, decision trees, and of course, expert vector machines. All of these could be treated in their own lecture of this one. I won't go in that level of depth, but just think of logistic regression as a generalization of linear regression, okay, that bounds the output, because like when you have a line, it's a line. So I could have negative output, I could have positive output. Negative output, I could have positive output way like towards infinity. With the ideal logistic regression, I want to bound this between 0 and 1 so that I have probabilities. With decision trees, it's like really intuitive. It's just, you already know what the decision tree is likely. In the sense that you just take your data, you split it, and then the rule that split that data, was it bigger than something, was it less than something, you just follow the path. That's the idea of decision tree. Random forest and gradient boosted trees, I'll let you learn that on your own, but there are two methods that build upon trees and that fix some of the issues. They fix them in different ways. Okay. And finally, we have support vector machines, which for a long time was like essentially the silver bullet for classification. Okay. It works really well if you have like data that is close to being linearly separable. Linearly separable just means I can separate them with a line. So now that you know all those things, hopefully, I'll ask you to just like stand up really quickly. I'll stand up because like I know it's a new attention. Oh, thank you, man. Thank you. So, take some space. And I'll just ask you to, take some space. And I'll just ask you to do jumping jacks with me for just a moment. Okay? And that way we're going to burn some calories, okay? Not going crazy, but it's okay. So, 3, 2, 1. Is everyone ready? There, okay. 1, 2, 3. Let's go. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20. Yes! Woo! Let's go! We're almost there, guys. We're almost there. Okay? So, I hope that... okay. I hope that you are all now awake for one more call. Okay?
Who's gonna carry the ball? He didn't tell us again. A lot.
So, now we're about to cover neural networks. Okay? Neural networks are like arguably one of the most important things like in machine learning right now. Like a lot of the time, if you're about to break something in like state of the art for something, you're probably using neural networks in some way. Okay? You're going to be using neural networks because of the different features we're going to be seeing here. First, well, then you can afford to be lazier, much lazier. In a sense that traditionally, if you're trying to like create a model for something, okay, you're trying to make it work for a given task. Let's take yet again the linear regression model. It's gonna want you to give something with linear relations with. So if there's no linear relations to be found, no matter what kind of data you give it, even if you yourself, as you're seeing, could like you clearly see that yeah, there's a relation here that exists that could be linear if I transform it that way, it won't be able to do it for you. So you'll need to do a lot of feature engineering a lot of the time for most machine learning models that are more classical. Okay? You'll need to like actually spend a lot of time just creating the best features to best take advantage of what your model can do. In neural networks though, typically you don't really need to worry too much about that. There's still gonna be some amount of pre-processing to do to like scale the thing, to scale the different inputs, and that's like mostly for gradients reasons that we'll see soon. Okay? But you can afford to be way lazier. The neural network, if you make it big enough, will learn those features on its own. So that's the first thing. Then they're really scalable. In a sense that like there's many different approaches to machine learning that if you give them too much data, won't really know what to do with it, or at least the algorithm will run, but will just be really slow. Super vector machines are a good example of that. Like if you try like running super vector machine on a big data set, it gets slow really quickly, okay? With neural networks though, they can take a while to train, yes, but they scale much better than other methods with data. Then, they handle well high-dimensional data. What I mean by that, by high-dimensional, is just when I give you data, like let's say, as an individual, like as a person, there's a bunch of data I could record about you. Your height, your age, your ethnicity, your, well, origin, that would kind of relate. Your blood type, et cetera, et cetera, et cetera. I could make a really big list, right? Most classical models, like a lot of the classical models, the more predictors I have, the more attributes I have, the less they're gonna work, okay? And they're gonna suffer from something called the curse of dimensionality, okay? Which is just the idea that the more dimensions there are, the more data I need to fill the space I'm in. Neural networks are able to, through the way they work, like the way the parameters work, are able to like skirt around that as well. And so they handle really well high-dimensional data. They're kind of a silver bullet, if you might say, because with a neural network, neural networks have a property that we call universal. Like, have you guys heard of the universal approximation theorem? You have. You just don't remember it. Have you heard at some point like a polynomial, for example, if you add enough like degrees, could approximate any function?
Yes.
That's universal. That's a universal approximation theorem. Neural networks can do that as well. But the thing is, polynomials like other universal I'm not saying that word again. Splines, for example, okay, don't tend to be either as scalable as neural networks or handle well-dimensional data like splines or polynomials, which don't do that really well at all, et cetera, which makes neural networks really good in like just a vast majority of contexts. And like, in fact, if you don't care about interpretability, about being able to like know why your model did the decision, like made the decision it made, neural networks are often the best there is. Okay. And yes. So yeah, there's like a caveat that should add that like there's some contexts where like still a machine learning model, like classical techniques, will still be really highly useful and like beat actual neural network. And those are typical cases where you just don't have enough data to make use of the advantages. If you know that something has a linear relation, you don't have to crack a neural network. You can just do a linear regression. Okay? So, a neuron is a glorified dot product machine. Okay? So I give you an input, I give you a set of weights. Those weights tell you, if you will, how important each input is to that specific neuron. Okay? Then, to that dot product, and like I say dot product because you could represent a neuron as like really just a vector, literally. Okay. Yeah. I will add a bias. The bias term, often called as well like the threshold of the neuron, is kind of just, you can think of it like the ymx plus b part. The b allows you to just model any line on the plane, right? It's similar to that, like the b allows us to have more flexibility. Okay. There's also a biological analogy, but I won't bother making it. But yeah. So when you combine multiple neurons, because like right now it looks complex, and like what we're going to be building is what you're going to watch the code for, and I'm going to share the code at the end, so like to just look at it and play with the neuron. It looks complex, right? But I told you that this here is a glorified dot product machine, right? And then you add some term to it, which makes it so that in the end, you output a number. This outputs a number. This outputs a number. This outputs a number. If I combine all of these neurons together, which yet again are all together vectors, into one big thing, that gives me a matrix, right? So each of these layers in a feed-forward neural network, that's the name of these, okay, will essentially just be a matrix. Okay? There's a big component that I haven't mentioned, which is the idea of an activation function. Think of it as the magical spice that makes it so this can approximate anything. Because without that, it's just all a big linear function, and then it doesn't really serve any purpose. It's just like ymx plus b all over again. Okay? So, that's where I start with the notebook. Okay, let's go. Did I send it there? Okay. So, do you guys know what Jupyter? Oh shit, I posted it. Whoops. Okay, no, it's still there. My bad. So. Okay. Okay. Whew. Who still remembers calculus? Who still remembers the chain rule? Okay, I want you to all clap for yourself right now. And you literally have 4 minutes to understand backpropagation. Okay? Backpropagation is fundamentally just an extension of the chain rule, but you're going to be working with matrices and tensors, like higher dimensional things, instead of just like numbers. Okay? So, we'll step through the code. If you have any questions, I'll try to answer them. But it really shouldn't. Yeah. Okay. So we start with importing the libraries I'm going to use. This entire neural network here is built in NumPy. Okay. It's all linear algebra. Here the goal is like really just to step through the logic. Okay. So we import NumPy as NP. There's a scaler as well, which is there to make sure. Like earlier I mentioned, like you typically want to scale your inputs to make sure that you have gradients that make sense. That's what that does. And then we have matplotlib, which to plot. Okay. Okay. Boom. What do we start with? The number of predictors, which tells us, in this case, 3 predictors, which are really just to map with the thing, the image we had before. Yes?
Are you able to zoom in?
Oh, my bad. Do you see that?
Yeah, thank you.
No problem. So you have that. You have number of outputs, which is 1. Yet again, mapped with the image. That's like a lot of those choices were just made to map exactly with the image. And then finally, the number of observations, which here is just because I didn't want to explain batching, and so I needed a data set that was big enough to learn, but small enough that I wouldn't need to like batch it on my machine. Batching is essentially when your data set is too big to run at once, instead of just loading everything at once, you just take parts and run through like by chunks essentially. Okay. So this part here is really just generating data. So then we create a random seed. Is because NumPy, instead of like just setting seeds, it uses the RNG object, and then from that RNG object, I'm just going to be creating like all I need. So my uniform matrices, my like all that stuff will be creating using the orange. Okay. The 1 to 3 doesn't have any meaning here, it just shows that. So then we have the set of coefficients. So why did I choose -10 to 10? No reason, I just felt like it. And so I get a matrix with a size of number of threads, 3, and number of outs. Here it's 1. It's coded to be generalizable. There's still some issues because like for that doesn't work. But yeah, in this case, since outs is 1, it's going to be a matrix that is 3 by 1. We have also our x, which is really just a set of our observations in this case, which is going to have a shape of the number of observations we have, so 1,000 rows and 3 columns. Okay, and finally we have the ones there. I think I don't even use it anymore, so I could have deleted that. Okay, I would for
The magic of Jupyter.
Oh, okay. So then we create a standard scaler, which will allow us to essentially scale the data to a scale that makes sense for gradient reasons. And I compute y, which is the thing that we'll try to get our model to learn. At this point, all we did was generating data. Okay. I've done nice plots for you. So I'll do that a little bit for the plots. Boom. Okay. So here we have the 1,000 observations. In blue, we have y against x1. You see the coefficient is 3.6647. We see like a slight linear trend. We have -8.924 here, so decreasing trend. And same thing here, decreasing trend, but like less strong. Okay. Could anyone try to tell me what would happen if that was 0? Like if any of these was 0? What would?
It would just be.
Yes.
Yeah, it wouldn't just be like a horizontal.
Exactly. So in this case, there wouldn't be really any information to be gained from the preliminary question because it'd be like 0 pretty much. Okay. So that's what we're trying to model. So now, let me just send that. So what are we doing? We're creating a matrix with a hidden dimension of 4. You saw earlier in the graph that we had like 3 inputs, which is why we had the number of threads of 3, and then 4 neurons per thing, right? That's our hidden dimension in this case. I need to make sure that every time I make sure to use like for this here, my out here is getting dim. So this was forced from the start because I need the output of this to be compatible with the output with the inputs of that. And since those are matrices, the way to make that work is for that dimension to be the same as this dimension. Okay? This you can mostly ignore it because in machine learning, the weights you start with can play a big role, and this is just like one way of initializing for values that work well. Okay? And so we're just literally just randomly initializing those weight matrices with W1 and then V1, which is our bias threshold. Okay? Then what do? We also define ReLU. A ReLU is really just that equation you see there. So you take a value, if it's positive, you return that value. If it's equal or less than 0, you return 0. Okay. Now, that's what forward pass looks like. Forward pass, as an expression, is just the idea that you take your input, x, and you make it go through the neural net. It looks magical when I show you a picture, but in code it's literally just that equation you're seeing here. I put x, which is my input here, multiply it. That's matrix multiplication by the way. Okay. So I multiply it by the weight 1, and then I add b1 to it. b1 here on its own doesn't have the right size, but it's broadcasted in such a way that the shapes will actually match. Okay. I recommend you to read up on broadcasting because that's something really important, but it just makes the shape work nicely. Okay. Then I apply ReLU to it. Then I do take the activation here, pass it to W2, apply ReLU to it. And then that's my predictor. I just take the output in the same direction. Up till now, that makes sense? This is what we call a forward pass. That's totally it. Take the left, pass it through the network. Okay? Then, what do we have? We have our loss function here. The loss function is the way you adjust to go back, like how you adjust your weights. The idea of your loss function is that you have your neural network. You have like a magical set of weights that does stuff for you. But you need to make it so, we're almost there, guys. We got this. You need to make sure that you can actually adjust those weights towards something that makes sense and that works for you. And so you need both a measure of how much you screwed up, which is your loss here, and then you need that loss to be differentiable. Because if you remember in calculus, how do you check the variation for one variable with respect to another? You take the derivative, right? And so that's why we take MSE. Strictly, it would have mattered what I used here, but MSE is just a nice one because it's easy to differentiate. And so right below, you see the definition of the derivative of MSE. And so now I'm just going to step through it quickly. If you have questions, you can ask me. The lambda function here is just like an anonymous function in Python, so now I can just use MSE and derivative of MSE directly with the brackets, and that's going to act as a function. Okay. So, what am I doing? I take derivative of y hat with respect to W3. I take first derivative of L with respect to y hat. Okay. Yeah, okay. So I take the loss, which I compute as the MSE. I take the derivative of that with respect to dy hat, okay? Which is, when you take the MSE, just take the derivative of a loss function, which is equal to,
What?
this is just equal to that here. Should be this, and the way I wrote this, or this. So you take the derivative of this with respect to dy hat, okay, and you get what we had before. Now I can just use this term on its own. I use the chain rule because I want to take the derivative of L with respect to all the parameters. But at this level, I don't have access to all the parameters, so I need to step through like that. Okay? So I will just do that, essentially. If you see anything that bothers you, just stop me. And yeah. So I take the derivative of dy hat with respect to W3, derivative of dy hat with respect to dv3. And since we have this one, we can multiply this derivative with the dy hat dw3 dy hat dv3 to get the derivative of dl with respect to dw3 and to b3. Okay? Then I just keep going that way. Boom, 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 boom. And so I know at this point you stopped listening to me like a few ages ago, so I'll just show you it works. Okay, that's the idea. Okay? You take your loss function. Yeah. So we start with a really big loss. And then as the epoch goes, okay, the more like we're gonna keep adjusting the thing and get towards a set of weights that just actually work for the data itself. And in this case, I didn't zoom enough for that. Yeah, almost like that. Let's see what it converts to. Okay. So it converts, it started with something like 110. It converts at the end at like 0.4 as an mean squared error. So we see that clearly we greatly decrease that as well. And so like that's really fundamentally the idea. You just apply the chain rule to stuff. I would like to go more in depth. I think what I'll do is like for a more in depth like disposition to backwarification as it deserves. You'll just have to come to a club meeting like Mondays 7 to 8. But yeah, that's the idea. So that's really it for me at this point. So yes, and I think that works for the time. So any questions?
I heard there's something called overfitting, and when you're doing gradient descent, so I think the cost actually goes up or something. Like, do you know how that works?
Overfitting is really just the idea I was mentioning earlier of the phi, that's